Hey, welcome! Today, we're jumping into a bit of soil science to cook up something really special, the recipe for Gley soil. Seriously, forget baking, we're talking about geology in the kitchen. So, let's get into it. So, here's the big question for today. How in the world do you get soil that's kind of bluish-gray, has flecks of rust in it, and is basically hostile to almost all life? I know, it sounds like something from another planet, right? But it's real, and we're gonna figure out this puzzle together. All right, here's our recipe card. First, we'll tackle the Gley soil puzzle itself. Then, we'll grab our ingredients, a very specific rocky foundation, and, you guessed it, a whole lot of water. We'll see how that mix creates a totally lifeless environment, and then, finally, we'll check out the finished product. So what is it that makes Gley soils so different? Well, it really comes down to one word: water. These soils are defined by being totally, constantly waterlogged. And that one fact kicks off this whole chain reaction that leaves them with barely any nutrients and some really, really strange colors. Okay, so every recipe has to start with a base, right? And for Gley soil, that base is its parent material, the rock that it comes from. And honestly, this is probably the single most important ingredient in the whole process. And that parent rock? It's clay. Not granite, not sandstone, specifically clay. And this one choice pretty much dictates everything that's about to happen, all because clay has one very, very important property. And that property is that it's impermeable. Just think about a clay pot or a ceramic bowl. You pour water in, and what happens? It just sits there, right? It can't drain through the bottom. Well, that's exactly what a clay foundation does in the ground. It traps water. And that's the absolute crucial first step to creating this waterlogged world. So, let's just quickly recap our base. We're starting with clay, which we know is impermeable. On top of that, the stuff is usually poorly weathered, which just means it hasn't broken down enough to release many minerals. So right from the get-go, we've got a foundation that's designed for bad drainage and has almost no nutrients to offer. So we've got our impermeable clay bowl ready to go. The next step is super simple. Just add water. But it's not just about a bit of rain. The environment itself plays a massive role in making sure that water doesn't just arrive, but that it sticks around for good. See, it's this combination that's the real secret. You start with that clay base, then you put it in a wet, often mountainous area where water naturally collects, and then, this is the clincher, you add cold temperatures. That cold is so important because it means very little water evaporates. The result? The soil becomes permanently saturated. It's like a sponge that you can just never, ever wring out. Now, being permanently waterlogged sets off this critical chain reaction. Because when water fills every single tiny pore and space in the soil, it pushes something else out, something absolutely essential for life as we know it: oxygen. And that lack of oxygen is a huge deal. You know, most healthy soils are aerobic. They have oxygen, which allows millions of tiny organisms, all that soil life, to breathe and do their thing. But our Gley soil is anaerobic. Without oxygen, it becomes this hostile place where all the worms, bacteria, and fungi that make a soil ecosystem work, they just can't survive. So what happens when you don't have those little critters to break down dead plants? Well, the organic matter just sort of sits there. The only things that can really survive in these harsh, wet conditions are stuff like mosses and lichens. When they die, they don't decompose properly. Instead, they just form this thick, dark, and really acidic layer on top called more humus. And here is the big payoff from all that. With no soil life to cycle nutrients and only a thin layer of moss to provide any organic matter at all, the soil becomes incredibly nutrient poor. I mean, it's a barren foundation. There's almost nothing there to support more complex plants. So yeah, you can pretty much forget about farming on this stuff. Okay, so we have mixed our ingredients, we've let the reaction run its course. Now it's time to pull our creation out of the proverbial oven and see what we've made. The distinct layers and colors of a fully formed Gley soil. All that water constantly moving downwards causes a process called leaching. You can think of it like this. The water basically washes any soluble minerals, especially iron, out of the topsoil, what scientists call the A horizon, and it dumps all that stuff into the layer below it, the B horizon. In these oxygen-starved conditions, this triggers a chemical reaction, oxidation. And what is oxidation? Well, it's just a fancy word for rusting.
The iron compounds are literally physically rusting inside the soil. And it doesn't happen evenly. It happens in these little patches, creating this signature red and orange speckled pattern or mottling all throughout that grayish-blue lower layer. It's the soil's most famous feature.
And here it is, our finished product. You've got a thin soil profile, because not much can grow. It has this silty, kind of slimy texture from all the clay. You get that dark acidic humus layer right on top, and of course, that telltale red mottling down below. And it's all defined by being poorly drained and extremely nutrient poor. What a combo, huh?
So, to wrap it all up, you can see how every single part of our recipe, the parent rock, the climate, the lack of living things, the type of vegetation, it all leads directly to a specific characteristic we can see and measure. It really is a perfect story of cause and effect out in nature.
And that kind of brings us to a final thought to leave you with. The entire existence of this soil type depends on this very delicate balance of water and temperature. So as our climate continues to change, maybe bringing wetter winters or warmer, drier summers, what does that actually mean for these unique ecosystems? Are they going to expand? Are they going to shrink? Or will they change into something else entirely? It's a really fascinating question to think about. Thanks so much for joining me for this one.